Okay, and we take you to practice quiz problem number 1. From memory, don't look it up. State the compound interest formula. And if you can't remember it, that's great. Put down what you can, maybe a variable or two. That'll be key information to help you remember and see what you could remember and what you need to refresh on. Okay, 30 seconds more. Right, this is the total amount you end up with is your initial principal that you started with times 1 plus the interest rate divided by the number of compoundings per year, all to the n times, it's either t or y, I forget which one we use, time or the number of years. Does anybody remember? Was it t or y?
I think it was T in the book.
Okay. All right, good. All right. And give me a little feedback on your remembering of this formula. Okay, go ahead and solve number 2. Okay, let me give you another minute. All right, let's start. So, in this part is the problem. The exponent is up in, the variable is up in the exponent position. So we're going to isolate the thing that I circled first, where the problem is. And that's going to be, what, 44. And then we're going to divide by 2. And okay, so now I isolated the problem area. So now I bring it down. And there's 2 ways to bring it down. One, you can write this as a log equation. Just rewrite it as a log equation. But more often, I'm used to doing something to both sides. So that's what I'm going to do. I'm going to do ln of both sides. Now, ln means log base e. I choose that because there's already an e in this. Alright, so then, now what happens to ln e? The unwritten base down here with e, and it's asking e to what power is this, and it's 3x plus 2. Or another way to think of it is these kill each other off, the inverse functions. And subtract 2. Divide by 3. This is what I call my exact solution. So if I was giving this answer to somebody who's going to do more computations with the answer, they'd probably want the exact solution so they can get as accurate as they need to be. But if they were going to cut a piece of wood this length or something like this, if they were going to work with this, I'd give them the approximate solution. So I'm going to punch this into my calculator. .36368, something like this. And how far you go in decimal doesn't really matter to me. I'm interested in do you have the basic idea how to do this stuff, and this is called the approximate solution. Alright, give me a little feedback on number 2. State the properties 1 through 3 of logarithms. Again, don't look them up. Exercise your memory. Thirty seconds more. All right, property 1. And you don't have to use B and M and M. You could use A and X and Y or whatever you want. When I make 2 logarithms out of 1, the multiplication that had to be there in the parentheses becomes an addition. If this had been an addition over here, we could not have made 2 logarithms out of 1. It had to be either multiplication or division. to be able to make two logarithms, and that multiplication or division turns into, in rule 1, addition, and in rule 2 turns into subtraction. Rule 3 comes up front. Okay, give me a little feedback on number 3, your recollection of the properties of logarithms. Okay, and once again, I'm going to mention that what's called the memory dump strategy. If you dump these rules down, then you have something to refer to, and when you do some tougher problems, you might need them. Alright, so go ahead and do number 4. .30 seconds more. Okay, let me have you stop. So, before I do this one, let me just emphasize something. If I had log x equals log of 4, if x was 5, no way these are equal. Plunge them out into your calculator, you get different values. The only way this could be true is if x and 4 are equal. How you can get from here to here is just say, well, these logically you could only be equal if it's 1 log and 1 log, then the things inside the parentheses have to be the same. But you could also do this giant 10 under here, because there was an unwritten base 10 here. And these would cancel each other out, and it would get you x equal 4. Alright, now that's the kind of thinking that I need to do over here. But the problem is, I have 2 logarithms on the right hand side. If it's 1 logarithm, you're okay with this. If it's more than 1, you can't use this idea here. If I had, let me just show you, 2 equals 1 plus 1. If I put a base 10, This is not true. 100, does that equal 10 plus 10? No way. You can't do this if there's two logarithms over here. Okay, so what I have to do is I have to combine these into one logarithm. Now, good thing I have the properties written down. If you ignore the test, just dump down the properties, so you've got something to refer to. Which property do I need? My first impulse is I need property 1. But property 1, the coefficients of these two are the same. There's really an unwritten 1 here and an unwritten 1 here. And I could use this property in the reverse direction, but only if this 2 was not there. So how do I get rid of this 2 that's there? If I divide by 2, I have to divide every term by 2, and it would put 2's in denominators where we didn't want them. But I can use property 3. I can use property 3 in this direction. The number out front can go up as the exponent. So this is log of this is equal to log of x squared plus log of 3. So that was property 3. I'm just going to put a little 3 above this equal sign to show that how I went from here to here was I used property 3. And then now I can use property 1. The m can be as complicated as you want. It can be x squared, and the n would be 3. So now I use property 2 to combine those two together. And actually equals now I'm going to use property 1 again in this direction. 2 logarithms into 1, so the addition becomes multiplication. When they become multiplied, I'll put 3 first. Like this. And let me show what property I'm using in a little different way. Get rid of this. From here to here, I used property 2. And from here to here, I used property, no, it was property 3. And then I used property 1 to go from there to there. And then, what's going to come next? Now I have 1 log equals 1 log is kind of like this over here. There's an unwritten base 10. These are going to kill each other off. They're inverse functions. And I am going to get this equation. Subtract 3x squared from both sides. Subtract 5 from both sides. Divide by 2. There is my answer. 2.5. So, give me a little feedback on problem number 4.
Wait, wouldn't it be negative 2.5 because you subtract 5?
Ah, thank you very much. So this negative negative 2.5. Oh, and then when I plug it in back here to check it, it doesn't work. I would get 2 log of negative 2.5. And then you're asking 10 to what power gives you a negative value, which doesn't work. 10 raised to any power, even a negative power, just gives you a fraction. So this, we have to throw the solution out. It doesn't check. And then we say that this equation has no solution. So who is that caught me on that? Good job.
It's me, Mushi.
Mushi, thank you, Mushi. All right, a little feedback on number 4. Write the distance and midpoint formulas with regard to the 2 points, x1, y1, and x2, y2. Thirty seconds more. So the distance formula, we say d is equal to the square root of the differences squared, and then this. And the midpoint formula, you average the x coordinates and you average the y coordinates to get the height that's just in between the two heights, the x coordinates that's halfway between the two, and so on. Alright. So those are the two formulas. Give me a little feedback on your recollection of those formulas. Number 6, write the two forms of equations of lines. There are two standard forms. Okay, 15 seconds more. They are y equals mx plus b and y minus y1 equals mx minus x1. Okay, write the 3 steps for finding the inverse of a function. Fifteen seconds more. Number 1, interchange x and y. You might have to replace f of x with y first, and that's kind of unstated. 2, solve for y. This is actually doing all the work. This has to invert every function, so whether it's addition, it becomes subtraction, all that kind of stuff. And it forces them to be done in the correct order. And then lastly, replace y with f inverse x. And then you've got your inverse function. Alright, give me feedback on 6 and 7, your recollection of those. Okay, and we are going to pick up where we left off. Well, last time we were in the middle of exponential and logarithmic models, and I hadn't assigned the homework because we hadn't gotten far enough. Quick announcement though, let me send you back to, we've got an exam coming up on Thursday. Well, that's the last regular day of class. So it's practice exam, exam 3 practice exam was due today. And then just today, what opened up is exam 3 practice exam with errors corrected. And if you go to here in the modules, you see that here it has the solutions. And then you can see the solutions, and then on the student version of this page, there's a button for uploading your corrections. So correct your own practice exam, redo the ones you did wrong, and then upload. You only have to upload those ones that you did wrong, or if you upload the whole thing, that's fine, but you only have to upload the ones that you had wrong. And also, in announcements, you might have already noticed math department activity. If you go to this announcement, this is from the math department. It's an activity that they want. We in the math department need you to click on this link and do this activity, and for doing so you get 5 points of extra credit. And so you have plenty of time to have it done by, but I would really strongly encourage people, if you haven't already done it, do it like right after class today. 5 points, it will bring up, you know, maybe your lowest homework real strong. And any questions?
What time will exam 3 start, and when will, like, how much time will we have to complete it?
Okay, so exam 3. So it goes from 1:15. So when on Thursday we will meet for half an hour from 12:30 to 1. We have a break to 1:15. From 1:15 to 1:45, so an hour, or to 2:45, an hour and a half, you have to take the exam. Anything else? All right, let's continue on then. In exponential and logarithmic models. And number 3, we're going to do part A together. Use the exponential decay model for carbon to solve the following exercise. All right, so when let me just kind of summarize real briefly. When we started this lesson, we had equations that might have looked like this: a equals 7 times 2 to the t. But then we said, hey, the standard way to model things is use a base of e. And so this is the standard modeling equation. A equals a0 e to the kt whenever you know something is growing exponentially, exponential growth or decay. So that's the equation that we model with. And we come down to here. Notice this is in that form. A equals a0 e to the kt, and the k is given. And use that to solve this equation. Prehistoric cave paintings were discovered in a cave in France. Originally, there were 400 kilograms of carbon-14 on the many cave walls. Now, due to radioactive decay, there's only 60 kilograms of carbon-14 on the cave walls. Estimate the age of the paintings. So, whatever the half-life was of the material that was used to make the paintings, we know that originally there were 400 kilograms carbon-14 in many cave walls. Now there's only 60. Estimate the age of the paintings. And A and A0 well, before I do this, there's 2 variables in this equation. A0 and E are not variables. They are constants. And that's different. Variables get to play the what-if game. They get to change, and when one changes, the other changes. So the 2 variables are T and A. And what I want you to do is write a brief description of what T represents and what A represents. And then go to your group chat and type in what what you have for T and what you have for A. And let's just check in on the groups real quick. If you are in group 1 and you're here today, I want you to join group 2. If you're in group 3, I want you to join in with group 4. If you are normally in group 5, join in with group 6. Alright, so everybody go into your groups. It'll be either group 3 or group 2, 4, or 6. And say hi. Group leader, make sure the spokesman knows who they are. And group 2, how many of you are here today? Nobody here from group 2?
This is Beverly.
There's 4 of us from group 2 today.
Okay.
Yeah.
There's 4 of us.
Great.
Mm-hmm.
Group 4? How many are here today?
2 people said that they're here so far. Oh, 3 people now.
Okay, 3. And group 6, how many?
There's 4 of us.
4 of you. Okay. Alright, go ahead and type in your description, a brief description of what T represents and what A represents into your group chat. Talk it out briefly. I'll call on a group in a minute. Okay, group 6. What is T representing?
One of us said that T represents the amount of years that have passed since, like, through the carbon dating.
T for time, and it's the years. Now, the years that have passed since when?
Since it was originally found, I don't know. Or, I mean, it says originally there were 400 kilograms of carbon-14. So since then.
Okay. Now, if we put it years since cave was painted. Cave was first painted. This would seem reasonable at first. I think, that seems to be the best description, but actually this is a really bothersome one, because when T is 0, I still don't know what time that was. Years since cave was first painted. So it seems to be a troublesome thing, but actually this is correct. Years since cave was first painted, because when it's year 0, we don't know what year that was, but the full amount of carbon-14 will be in the paint. Carbon-14 is something that is in a whole lot of substances, and lots of living things have some carbon-14 in them. And then they probably made their paint from some living things. And so this would be correct, and as time goes on, as the number of years goes on, this gets we get less and less of the carbon-14. If the half-life of carbon-14 is, let's say, 5,000 years, then in 5,000 years, half of the original amount will be there. Okay. Now, what do you have for A?
I mean, we didn't really come to a consensus, but I guess the age of the paintings, I'm not sure. Because that's kind of the same thing as time.
Ah, okay. That's a neat observation. Kind of a nice impulse, A for age of painting, but if you do that, it's just repeating this one. So we need something different. So what else could it be? What might A represent? I'll open the floor to anybody. Anybody have any idea? Let me focus you on this. Originally, there were 400 kilograms of carbon-14 on the many cave walls. And then later, there's only 60 kilograms of carbon-14. The number of kilograms of carbon-14 on the cave wall seems to be changing. It seems to be going down. Originally, there was 400. Later on, there's only 60. So a brief description would be, anybody?
Is it like decay?
So yes, something is decaying. What is decaying? On the right track.
The carbon-14?
That's right. So A, typically, T typically stands for time. A typically stands for amount. Amount of carbon 14 on the cave walls in kilograms, because they say it's in kilograms. Right. These are the two variables in this. Once we have the variables, we can go about doing this. Originally there were 400, this part right here, there were 400 kilograms of carbon-14. Now, change that into math. Originally means, well, time since the cave was first painted. When the cave was first painted, what was the time? 0. Because that's when we start the clock. Years since the cave was first painted. When t equals 0, A was 400. So we translate this sentence into looking at the variables, what it means. All right. Now when we take these two and we plug them into this equation, plug into so 400 goes over here. 0 times anything is 0. And what's anything to the 0 power? Anything to the 0 power is 1. So what does it tell us? It tells us that A0 is 400. Now I just figured out A0 the long way. A0 also represents an original amount at time 0. So I could have just jumped into and said A0 is 400. But I could have done it this way as well. Plugged in when t equals 0, a is 400 into this thing, and it tells you what this unknown constant was. All right. So this right here we call the general modeling equation. We go from the general modeling equation to the specific modeling equation when we just figure out what the constants are in this. The specific modeling equation is you leave the variable as variables. A and t stay A and t, but we replace the A0 with its known value now. Now, the true general modeling equation would add a k in front instead of this negative 0.000121. But that was given. Once you found both the k and the A0, you have the specific modeling equation. Now it says, and once we get the specific modeling equation, we can answer any questions. It says, now due to radioactive decay, there's only 60 kilograms of carbon-14 on the cave walls. Estimate the age of the painting. Where does this 60 go? 60 is the, since it's kilograms of carbon-14, I just looked, it's not T, it's A. 60 is the A, so we just plug it in here. And then we have to solve this equation. Now, you're going to come up with exponential or logarithmic equations to solve. Good thing we've been doing that recently. So I'm going to divide both sides by 400. And turn that equation around. 60 divided by 400, I'll do my calculator. 0.15. So then I'm going to take the ln of both sides, because that exponent is in a nasty, the variable is in the nasty position of being in the exponent. And after I take the ln of both sides, I get to use property 3 to pull this down. Or I could have just said these two kill each other off, because ln e is saying what is the exponent on top of e that gives you a result of e, and so this part is just 1. That is equal to ln of 0.15. And then I'm going to divide both sides. And then my t will equal, and I'll punch this out on my calculator, ln 0.15. And I get So, what's the meaning of this T right here? Well, that's how many years have passed? A little more than 15,000 years has gone by since the cave paintings were first painted. Any questions on 3A? All right. We are at a break point, so let's start again. At 1:37 p.m. Does anybody need to speak with me individually before I take my break? All right, see you in a bit.
masks are required. So I'm just assuming that it's open. We can try it.
Okay.
But I sent an email over to Monaco, whatever it's called, but they're over in Nevada, and then they forward my email to whoever is in charge. And I just said it is, is it unlocked? Okay. And then I went out and saw that the clock is okay, and you can't go.
Yeah. I am teaching the course. We're taking a break right now. We take a 15-minute break in the middle. I finished at 2:30. If it's blocked, maybe we could go down to the train park. Yeah, maybe that would be okay.
Yeah. Let's try something.
Okay, so I'll see you out at the courts here at 3 o'clock.
Okay.
Sounds great.
See you, Bob.
See you, Don. See you, Don.
Take care.
Okay, bye-bye. Can I stop? right, we shall start up again, and I can't remember if I mentioned this already in the announcements. Math department activity. So if I mentioned it already, please forgive me, but please do this activity. Click on this link, do this activity. You'll get 5 extra credit points for homework. Be applied to your homework for doing this activity. So it's a top announcement. And let's continue on. And we're going to go to 3B. Skeletons were found at a construction site in San Francisco in 1989. The skeletons contained 88% of the expected amount of carbon-14 in a living person. In 1989, how old were the skeletons? So we'll work this out together. Now what I'm working on is your homework. I copied the homework onto here, and so if you get in the modules, you'll see this sheet, and certain one of these problems will be done for you because we'll have worked them together. There'll be plenty that I'll leave for you to do on your own. Okay, so in this situation, we're going to set it up with the same variables. T and A. How old were the skeletons? And T is going to be similar to what we did in the last one. It's time. Years. Now, how old are the skeletons? I think since the question, we usually figure out our variables from the questions that's asked. Years, I think it's before 1989. So how old are the skeleton? If we got, 1,000 for T, that would mean it's 1,000 years old. And then the A is again going to be the amount of carbon-14 in kilograms. And what we're going to do is the general modeling equation. We know that the amount of carbon-14 decays exponentially. So it's exponential, so we use the general modeling equation. A equals A0 e to the k t. Now the pattern we're going to wind up getting into with these problems is we need to find the constants A0 and K to get the specific modeling equation. And sometimes you can find both A0 and K, sometimes you can't. And sometimes you live with what you can find. Alright. The skeletons contained 88% of the expected amount of carbon-14. Alright. Now, it says to continue to use this modeling equation. The exponential decay model for carbon-14 was this one. So we should replace the K with this number. Now, if we replace the K with that number, we come out with this modeling equation. And now we're dealing with this thing. The skeletons contained 88% of the expected amount of carbon-14 in a living person. So, what do we put in to this equation having to do with this 88%? Where does that go into this equation right here? So that's the question I'm going to give for each of the groups. And when you have any ideas, type it into your group chat. And I'm going to call on a group in a minute. Where does this contain 88%? How do we plug that into this equation when we know all this stuff? I'll give you a little bit of time to think that over and communicate with each other. Okay, group 2, any ideas of what to do with this 88%? Even if it's just a total guess, it will get us at least moving. Group 2, you can always say pass. Any ideas? Let me just check on group 2 over here. Anybody here? Alright, no activity for a while. Alright, let's go to group 4. Any ideas with the 88%? Anything? Again, you can just pass. Let's go to group 6. Anything?
When you plug in 0.88 to A,
And you're gonna okay, this. Now this, what you just said, is the most common student reaction to this. And it's close. But for instance, if the original amount, A0, let's just say for instance, if A0 was 100 kilograms, it didn't tell us what the original amount was. But suppose it was 100 kilograms. What's 88% of 100 kilograms? It would then be 88, because you take that 0.88 times 100. It's 88% of something. And so if you did it like this, if that was 100 kilograms and you put 0.88, that would be, less than 1% of that. So you gotta multiply it by the times the initial amount. And what's the initial amount that goes in this parenthesis? Group 6, what do you think? What goes in there?
what do you mean? I'm a little confused.
All right. How much did we originally start with?
We don't know, do we?
That's correct. We don't know. But what are we calling it?
Just the expected amount of carbon. So
A sub 0.
okay.
A sub 0 is the amount at time 0 or the original amount. And when t is 0, this part becomes 1. And 1, so A becomes A equals A0 in that case. All right. So if this part was, if this was 100, then this would be 88. And so whatever the A0 is, if it was 100 times 0.88 would give me the 88 kilograms that I would need over here. All right. So this 88% of the expected amount gives us this. Now, here's the crazy thing, is we never know what A0 is. They don't tell us what we started with, but we don't need it. In the equation, what's going to happen is this. You divide both sides by A0, and it completely drops out. You get 0.88 is e to this right here. And then we have to solve this equation. Now, to solve this equation, we are going to take the ln of both sides. And then this part is going to come down. Or the ln and the e kill each other off. And so we get, and then I'm going to turn it around, negative 0.000121t is ln 0.88. And we divide by this. And then what we get is us our exact answer. And then, if we punch it in our calculators, we get 1056.47. So that's the answer for T. And so how old are the skeletons? The skeletons, worded problem needs a worded answer. Approximately 1056 years old. All right. And any questions on B? All right, let's go to 4A. And put a bunch of space in between there. Now it says use, they don't give you the K this time. Use the normal exponential decay model, A equals A0 e to the kt, to solve the following exercises. Round the answers to one decimal place. So the half-life of thorium-229 is 7,340 years. Okay, now let me describe what this means. In 7,340 years, you will have only half of your original amount remaining. Okay. And and every time 7,340 years more passes, that half gets cut in half, 1/4, and it gets cut in half again, 1/8, so on. All right. How long will it take for a sample of this to decay to 20% of its original amount? All right, so we're going to start with the general modeling equation. Whenever we know that has exponential growth or decay. Now, what's our initial task? First task. And remember we call this the general modeling equation. The first task is to use the half-life info to find A0 or K. We've got to get the two constants, and once we get whatever we can of these, if we can get A0, we do A0. If we can't, we at least get K, and then we'll get the specific. Thus getting the specific modeling equation. All right, so I'm going to make a little table T and A. When time t is 0, it zeroes out this, because e to the 0 is 1, so a would be a0. We don't know what a0 is. But we have a variable for it, or a constant for it, which is called a0. When t is 7,340 years, we are going to get 1/2 of the original amount. Alright, this one is telling us when t is equal to 7,340 years, a is equal to 1/2 of the original lot. Okay, we're going to put that into this equation, the general modeling equation. So this goes in here. Goes in for the A. And what I get is 1/2 a0 is equal to a0 e to the k times 7,340. Alright, now notice I'm never given in the original problem, never given how much I started with, how many kilograms. It doesn't tell us. Turns out we don't need it. There's no way to solve this for a0, but the a0 just divides out. And you get, well, I'm going to call it 0.5. I'm going to put this number first. Okay, and then I need to solve for k to get the specific modeling equation. Okay, so now I'm going to take the ln of both sides. These will cancel. Turn it around. And then I'm going to divide both sides. 7,340. And k is this. Let me punch it out on the calculator. ln 0.5 divided by 7,340 is negative 0.8. 4 zeros. 9, 4, 4, 3, 4, like this. Alright, now I can write my specific modeling equation. I can't get the A0, so I leave it as A0. But I'm going to replace the K with this. So the specific modeling equation is always the same as the general modeling equation, but fill in either A0 or K or both, whatever you can find. Okay. Now, so what we did is we just used the half-life information first. That was important. The half-life of this let us find K. And now I'm going to go to the next part. How long will it take for a sample to decay to 20% of its original amount? Alright. How long to decay to 20% of original amount? When it's decayed to 20% of its original amount, the A will now be what most students want to do is just plug in 20%, 0.20. But you have to multiply it by the original amount. We get this. And then I divide by A0. And we get 0.20. Oops. Equals e to this. And then I have to solve for t. So I'm going to take the ln of both sides. Ln and the e kill each other off. I'm going to get this equation, and I'm going to turn it around. And then I'm going to divide by this constant. And then I'm going to get, that's the exact answer, and if I punch it out, well, it's not exact because it's got a, I rounded off with 0.4, 0.000944434, but if I punch this out, I get So it took approximately 17,000 years for it to decay to 20%. Now notice, if it would have decayed exactly, if it would have been for 7,340 years, it would have gone to 50%. Another 7,340 years, it would have gone from 50% down to 25%. So that's around 14,000, two of those 7,000s. And then a little bit more than that, 17,000 to get all the way down to 20%. All right, so that's how we do these, and that finishes up this section, exponential and logarithmic models. Any questions? Okay, so the homework is 6.7 replacement problems. If you go into the 6.7 homework in the modules in Canvas, it won't tell you problems to do in the textbook. It'll just tell you, here, this worksheet, do this worksheet. And it's these problems, but you have to do all the rest of them. So there's a bunch of them in here that are somewhat similar. Oh yeah, I wanted to do number 5. Let's look at this one. Number 5, use the exponential growth model, the standard one, to show that the time it takes a population to double, to grow from A0 to 2A0, is given by this formula, t equals ln 2 divided by k. All right. We'll do this one together here. So the original modeling equation is this. The time it takes to double double the initial population is the doubling time for all exponential functions is a constant. No matter what the exponential function was, the doubling time is always the same inside of one specific application. So the time it takes to double the initial population, we don't know what it is, but the idea is solve for t when a is replaced with 2A0, with twice the initial population. So I'm going to go over to here. And I'm going to, when I see the A, I'm going to put 2A0. And now I'm going to solve this for k. Alright, if I'm going to solve this equation for k, first thing is I'm going to get rid of the A0. I get 2 equals e to the k t. Then I gotta continue solving it for k. So what am I gonna do? I gotta get the k is up in the exponent position. So I gotta bring it down. I take the ln of both sides. And these kill each other off. I'll put the kt to the left and the ln2 to the right. And then I divide both sides by t, and I get k equals ln2 divided by t. And I did exactly what was asked. And I showed that that's always going to be the case. Any questions on number 5? Alright, let's go to number 6. Use this model to show that the time it takes population to triple is given by this. We're going to do the same thing. The time it takes the population to triple is we're going to replace A with 3A0. And then you get 3A0 is A0 e to the kt, and you solve for k. And we are out of time, so I will leave that up to you. But that's the idea on these last two.
Mr. Shankin,
Yes.
can I talk to you about some stuff when everyone else is dismissed?
You bet.
This is Beverly.
Okay, you bet. Are there any questions? All right, so the homework then is this, and this applications of logarithms is not going to be on this exam 3 because we just got to it. It'll show up on the final exam, but it won't show up on exam 3. So, and since we got to it a little late, I'm going to extend the deadline so that 6.7 will be turned in later. I'll have that due by the time of the final exam on December 10th. All right. So we'll stop here. Let me stop the recording.